In section 5.7, we're going to be using the cross product to determine different things. And first thing we need to do if we're going to take the cross product of vector v and vector w is we need to put these vectors in a matrix. So I have my I, j, and k components, and so I'm going to take my values here and plug them in. We have 3, 1, and 3 going across here for vector v, and then for vector w I have 1, 0, and -1. So when we're talking about doing the cross product, remember what we're really looking at, if the A values are the I components and my B values are my J components and my C values are my K components, what we do is we're going to actually take, just like doing determinant, if I'm talking about the I component here, I will just do determinant of the B and C values. So for example, here when we do this cross product, I would take B1 times C2 minus B2 times C1, and that would give me my I component for the cross product. Then we say minus, and now for the J component, forget about those B values, and now we're going to take A1 times C2 minus A2 times C1. That's an A. All right, and that gives us our J component. And then we have plus. And then for the K component, forget about those C values now, and now we're using the determinant here between A and B. So we have A1 times B2 minus A2 times B1, and that gives us our K component. So now for to actually plug in those values, what I would have is my B1 is 1, C2 is -1, and then B2 is 3, C1 is 0. And so when I multiply those together, I have -1 minus 0 gives me a -1. And remember, that's our I component. Now we have minus, so A1 is 3, C2 is -1, and A2 is 1, and C1 is 3. So now when we multiply here, we end up with -3 minus 3 gives us -6, and then this is minus, so it actually turn into plus 6, and that's our J component. Now we have plus, and A1 is 3, B2 is 0, so that'll go to 0, minus A2 is 1, B1 is 1, and that gives us our K component, and that would be equal to -1K. So the cross product gives us a vector, and here's that vector. So what I want you to do now is let's look at the cross product of vector W with vector V and see how that compares. Because now when we set up our matrix and we look at our I, J, and K components, now we're going to switch. Instead of having 3, 1, and 3 here, and then the 1, 0, and -1 here, we're switching places with those. So now we'd have 1, 0, -1, and 3, 1, 3. And so let's go through, let's do the cross product of those two and see how they compare. So for this example now, we've plugged in our values. So here we have 0 times 3 and -1 times 1 for our I components gives us a 1I. Now plugging in a 1, 3 and a -1, 3 gives us 6J, and then 1 and 1 here, 0, 3 gives us 1K. So we have I minus 6J plus K. So if we compare the two cross products, notice that our signs have switched. So that's one of the properties that we're going to talk about, is that when you look at the properties of cross products, that if we have vector v and we're taking the cross product with vector w, that's going to be equal to the opposite of vector w and cross product with vector v. Also, if we take vector and we take the cross product with itself, that'll equal 0. And if we take some value, some constant, times the cross product of vector v with vector w, then we would have that constant times vector v with the cross product of vector w, or could also say we've got vector v cross product, and we could take that constant times vector w. And if we have 3 vectors, if we have vector u, and we're going to take the cross product with the sum of vector v and vector w, we can take the cross product between u and v plus the cross product between u and w. Also, as I mentioned before, vectors v and w, to be able to do the cross product, they must be vectors in space. We're talking about something that's three-dimensional. And the cross product of v and w is also a vector. And it is perpendicular to both of those vectors, both v and w. Also, if we take the magnitude of the cross product, that is equal to an area of the parallelogram that is created with vector v and vector w as adjacent sides. And if the cross product of our 2 vectors is equal to 0, that happens if and only if v and w are parallel to one another. Here we're given points 1, 2, and 3, and we're going to determine a parallelogram with those. And so we're going to have point 1 be our common point here. So these would be 2 adjacent sides of a parallelogram. And so let's have point 1 to point 2 gives us vector v. So to determine what that vector would be, I'm going to go from point 2. We're going to find that position vector. So I'll take 5 minus 2. That gives me 3i. Then I have 1 minus a negative 1. That goes plus 2. That's my j component. And then 4 minus 1 gives me plus 3. That'd be my k component. And from point 1 to point 3, let's have that be vector w. And so same thing here. Now I'm going to take point 3 minus, so I have 0 minus 2 gives us a negative 2 for the I component. 1 minus a negative 1 gives us plus 2 for our j. And then 1 minus 1 gives us 0 for that k component. So now as far as finding the area of that parallelogram, if we find the magnitude of our cross product, that's going to be equal to this area. So first we need to find the cross product of v and w. And so again, I'm going to take my I, j, and k components, and we have 3, 2, and 3. And then here we have negative 2, 2, and 0. And now we're going to take the cross product of this. So we would end up with 2 times 0 minus 3 times 2 for that I component, minus 3 times 0 minus 3 times negative 2 for that j component, and 2 times negative 2 minus 3 times 2 for that k component. So that is going to give us negative 6i minus 6j plus 10k for the cross product. So then to take the magnitude of our cross product, well, we know to take the magnitude, we're going to take the square root of, and we're going to take our 6 squared. It's a negative 6, but we're squaring it so it becomes positive anyway. Plus our 6 value here, squared, plus 10 squared. So we end up with 36 plus 100, or square root of 172. That would be the area of the parallelogram determined by those points.